All right, so looking at this question, we've got two acidic solutions, HClO4, which is going to be a strong acid, and then HClO, which is going to be a weak acid. That's why we have the Ka provided there. So if we think about what's actually going to occur with this reaction, since the HClO4, that perchloric acid, is going to be strong, when we take it and dissolve it in water, we're going to get complete dissociation. So we'll get 100% essentially of those two ions, including that acidic H plus. So if we wanted to get the pH of the solution, we can just do pH is equal to negative log of the hydrogen ion concentration there, H plus. And in this case, since the solution itself is 0.1 molar. Oh, and I guess actually for this one, we don't even need to ultimately calculate the pH. But for the first one, the concentration of that hydrogen ion is just going to be 0.1, 0.100 technically. But that's just going to be because the solution itself is going to completely dissociate, whereas the HClO, we're going to have a reversible reaction there. We're going to wind up with an equilibrium because this is going to be a weak acid. So we're only going to get a small amount of those ions being produced. And if we think about it, we'll start, if we have our ice table, ICE, we'll have 0.100 molar to begin with. And we'll have 0 of the hydrogen ion, 0 of the accompanying anion. And then when we have this dissociation occur, we'll have some amount of plus X. That's going to be the amount that those will change. And then the original substance is just going to decrease by that same amount since everything's a 1-to-1 coefficient relationship. So at equilibrium, we'll have concentrations equal to X on the product side for both of those ions. And for the HClO, we'll just have the original concentration minus that change, so minus X. And for this one, we're going to be able to make it a little bit easy, just like we've seen with some of the previous examples, because this Ka, this acid dissociation constant, is very small. So X is going to be a very, very small number. So it's essentially going to be negligible when we're comparing it to the initial concentration of the HClO. So we're going to essentially be able to remove that from the bottom of our equilibrium expression. So we'll set it up 2.9 times 10 to the, and let me switch stylus so it's a little bit easier, 10 to the, what is it, negative 8. And we'll have that equal to X squared on top because it's going to be products. And then, like I said, we can make it easy and just essentially remove the X from our denominator there because it's going to be so much smaller compared to the original concentration. So when we go through and actually solve for this one, we're going to see that the hydrogen ion concentration, which is what X is going to represent, as well as the anion concentration, is going to be 5.39 times 10 to the negative 5th molar. And again, with this one, we're just taking advantage of the ice table, thinking about equilibrium. When we take this substance and dissolve it, some of it's going to dissociate. That's what we're representing with the variable X. And then we can plug it into our equilibrium expression, where it's products over reactants. And then we have X squared there because we've got both of those ions. And they're going to have the same concentration because everything's 1-to-1 relationship. So at that point, it's just a little bit of algebra, cross multiply, and then take the square root to get the concentration we see there. And then with the next one, we're thinking about the percent ionization. So again, niacin is going to be a weak acid. I forget the exact structure, but it's like a benzene ring with, I want to say, a nitrogen coming off of it, maybe amine. I forget exactly what the structure is. But for this one, we've got essentially the same question, but kind of twice, because we're looking at the percent ionization of this substance, but with two different starting concentrations. So when we're setting this one up, it's going to look very similar in each case. It's just going to be what we plug into our ice table. Oops. I can get the stylus back, which go. So with it, again, we'll have I'm just going to do H, and then we'll do X just for the acid, because I don't want to write the entire formula. But we'll get some of that hydrogen ion. we'll get X minus. So we can do our ice table. And then if we're looking at 0.020 to start, we'll have 0 of the products. And just like the previous one, oops, that should be plus X minus X. And again, we've got a pretty small acid dissociation constant. So if we wanted to, we could keep the X in there, do the quadratic formula, or we can just kind of simplify it a little bit. So I'm just going to have 0.02 on the bottom again. So 1.5 times 10 to the negative fifth. And that's going to be equal to X squared again, because we just have H plus and then that ion on the right-hand side. 0.020. And then when we go through and actually solve for this one, what we're going to see is that we get a, where's my math? 0.00055. So that's going to be the concentration of that hydrogen ion. So if we want to get the percent ionization, changed. So percent ion, it's going to be H plus, oops, over HA times 100. And what that's referring to is the hydrogen ion concentration, so H plus on the product side, and then HA is just representing whatever that acid's going to be. So in this case, it's going to be the niacin, it's going to be the 0.02. So if we take the 0.00055 that we just solved for, plug that into the numerator on top, take the original concentration, plug that into the denominator on the bottom, what we're going to see in this case is that of that original molecule, 2.8% of it is actually going to ionize. So if we had 100 of these molecules, about 3 of them would actually wind up dissociating into that H plus. And then for the second one here, if we did the 0.010, it would be the exact same setup. It's just the only thing that would change is we would have 0.010 there, 0.010 there. And then when we go through and actually solve for it, what we'll see is that in that case, we get 0.00039 molar. So when we plug it in for the percent ionization, that'll be what goes in for H plus. 0.010 is going to be what's going to go into the denominator. So in that case, what we're going to see is the percent ionization is going to be 3.9%. We get a slightly higher percentage of that substance ionizing in that case. But the general setup, general calculation is going to be the exact same. It's just we've got a slightly different initial concentration. So when we plug it into our equilibrium expression, the denominator would just be 0.01 instead of 0.02. But we're still going to have X squared on the top. We still have the same equilibrium constant for Ka. So we're just solving for that new hydrogen concentration, solving for the new ion percent ionization. And then with these acids, for the most part, what we've looked at, if we think about something like nitric acid, hydrochloric acid, those are going to be monoprotic acids, meaning that they've got one ionizable hydrogen. So if we think about the formulas for those, HCl, HNO3, each of those, when we take those substances, they're strong acids that are going to fully dissociate, but we only have a single proton there. We only have that single H in each of them. So we're only going to get a single H plus with each of those molecules. But if we think about something like H2SO4, now it's got 2 of those hydrogens there for every molecule. So we're going to get 2 of those protons when this substance dissociates completely. And then phosphoric acid isn't a strong acid, but it does have 3 ionizable hydrogens there. So we could get 3 of those H pluses. And the last 2 examples there, the sulfuric and the phosphoric, those are going to be examples of these polyprotic acids. And similar to what we're looking at the bottom with carbonic acid, these substances are going to have a different equilibrium for each of those different ionizations. So if you look at the carbonic acid, H2CO3, if it gives up that first proton, it still is HCO3 with the negative charge there. So that's why we've got that second dissociation. And with each of these, we're going to have a different dissociation constant. So if we had the values for these, we might call the first one Ka1, because it's the acid dissociation constant, but it's going to be for that first dissociation. And then the second one would just be Ka2. Phosphoric acid, H3PO4 would have Ka3 as well. And what we're going to see with most of these polyprotic acids is that first dissociation constant is going to be much greater than the latter ones. And that's going to be kind of the most important dissociation, I guess. But we'll see an example of that, I think, right here. Yeah. So if we look at that one, we're actually going to look at carbonic acid a little bit in this question. But the solubility of carbon dioxide in pure water at 25 degrees and 1 atmosphere, or 0.1 atmospheres rather, is 0.0037 molar. And then with it, it is common to just assume any dissolved carbon dioxide is actually going to be in the form of H2CO3, so it's in the form of carbonic acid. And you can see the reaction that's going to occur there, which is going to essentially take carbon dioxide and water, put them together to give us that carbonic acid. And what we want to do is figure out what is the pH of a solution that has that much carbon dioxide actually dissolved into it. So we've got that 0.0037 molar. We could think of that as the concentration of carbon dioxide. Like I said earlier, though, we can also just directly assume that's going to be the concentration of carbonic acid. So with this one, oops, I don't know why this is there. Screen. So with this one, what we see is H2CO3. And if we think about that first dissociation, we're going to have H+. We're going to get that first hydrogen ion. And then we're still going to have, whoops, I forgot the H there. Still have a hydrogen there, so that's going to be the hydrogen carbonate ion, or the bicarbonate ion. Represent the same thing. So it's still giving me that little. So, and for this one, what we need to know is the equilibrium dissociation constant. And for this one, Ka1 for carbonic acid, let's write that down, 4.3 times 10 to the negative 7th. And then the initial concentration of the carbonic acid, 0.0037. So with this one, we can treat it exactly the same, but then we're going to be able to see with the, we'll go one step further with this one. But initially, we can treat this just like the previous ones. We'll have 0 of the hydrogen, 0 of that bicarbonate to start. And then that'll increase by plus X. This will decrease by negative X. So we'll wind up with 0.0037 minus X. And when we go through and actually plug that in, again, Ka1, that would just have to be given to you in the question, so it wasn't actually provided on the previous slide. But that's just either 4.3 times 10 to the negative second. That's going to be the acid dissociation constant for this initial ionization, initial dissociation. And Again, since that equilibrium constant is very small, we can assume that the change in that initial concentration of carbonic acid is going to be negligible. So that's why in the bottom there, I just have 0.0037. We could include the negative x and go through the quadratic formula. Ultimately, it's not really going to affect our answer at all since the equilibrium constant is so small, meaning we're only going to get a very little amount of this reaction actually move to the right. So we can just set it up like we have here, do that cross multiplication, take the square root, and what we're going to see is that the concentration of that hydrogen ion is incorrect. So let me pause this and double check that. All right, and then with this, so it's going to be 10 to the negative. This. That's going to be the hydrogen ion concentration. So remember, pH is going to be equal to the negative log of that concentration. So what we're going to see here is that the pH of this solution is going to be 4.40. And again, this one pretty much the same as the previous types of questions we've seen here. But what we can do now is go actually one step further. So we can look at that second dissociation. And what we're going to want to do is just keep this, keep that information there. So that'll be the hydrogen concentration. That'll also be the bicarbonate concentration. So when we look at the second dissociation, now we're taking that bicarbonate that we just produced with the first one, and we're going to go one step further and then have that second hydrogen now dissociate. So that's why on the right-hand side here, we've got the hydrogen ion, we've got the carbonate now, just so it's CO3 2 minus. And in this case, we've got the initial concentration of the bicarbonate, just going to be the previous value that we had. So it's going to be this 4 times 10 to the negative fifth. And then that's actually going to be the initial concentration of this hydrogen ion as well, because that was also produced, even though it's not this hydrogen, there was also hydrogen ions produced in that previous step, previous dissociation. So we're going to still have some of those ions present, and then we'll have none of the bicarbonate initially. So what we're going to see is we'll have, again, plus x, and actually I'll change this to a different variable just because we had x for the previous one. So let's do z, and then this will be negative z. And just like the previous one, we need to know the equilibrium dissociation constant for this one. So Ka2 is going to be even smaller. So the previous one was 4.3 times 10 to the negative 7th. This one's going to be 5.6 times 10 to the negative 11th. So we're going to get a very small amount of this reaction actually pushing to the right-hand side. And with this, I'll now erase what we have at the bottom. But with it, you'll notice for the equilibrium concentrations for the carbonate and the hydrogen ion, I didn't even bother to include the z in there at all. So negative z for the left-hand side, positive z for the right. Just because this reaction is going to move so little to the right that, again, those concentrations, the change in them is going to be negligible. So it's essentially going to be that same thing as what it is initially. So if we think about what we're going to have here, we can set this equal, so that's our equilibrium constant. We'll have products over reactants. So we'll have 4.0 times 10 to the negative fifth times z. And then on the bottom, we'll have 4 times 10 to the negative fifth. So what we're going to see here is those are going to cancel. And we're going to see z in this case is just going to be equal for that second equilibrium dissociation constant. So it's just going to be equal to 5.6 times 10 to the negative 11. So we're going to get a very, very small amount of that carbonate ion actually being produced here. And then with this reaction, with this carbonate ion, be the carbonic acid, be the carbon dioxide, that whole sort of system that we're looking at here. So again, carbon dioxide dissolves into the water, produces carbonic acid, dissociates to give us H plus, lowers the pH of that solution. This is going to be environmentally an important reaction, just because it's going to affect the pH of the ocean. So as we burn fossil fuels, we produce more and more of that carbon dioxide. It can then dissolve into the water, make that ocean acidic, and then that has, of course, consequences for all living organisms in that water. But especially with things like coral reef and mollusks, things that use carbonate to actually make their shells and survive. That equilibrium is being affected by that additional carbon dioxide, by that decreased pH, and it's making it more difficult for them to actually form those shells, so they're not surviving as well. And again, that's just going to be one of the many consequences of climate change, of course. Okay. And then as we look at the next piece here, weak bases accept hydrogen ions. So if we just think about the definition of a base, it's a proton acceptor, so it's going to gain that H plus. That's why if we look at something like ammonia here, NH3, we put it with water, it's going to take one of those hydrogens basically from the water molecule, make it the ammonium ion, NH4 plus, but that's going to change water into OH minus. So we're going to see a small amount of that hydroxide form, and that's why we're going to consider ammonia to be a base, even though it doesn't have OH in the formula. And if you look at the concentrations there, we can see initially we're going to have entirely ammonia. And again, we're not looking at the water at all, just because that's going to be a pure liquid, so the concentration is not actually going to change. But with the ammonium ions and the hydroxide ions, we can see we get just a very, very small amount of those. Whereas the ammonia, we still have pretty much all of it to begin with. And with this reaction, the base dissociation constant is just going to be 1.76 times 10 to the negative fifth. We're going to be able to use that to do quite a few things. We'll actually be able to wind up relating that to the acid dissociation constant for the reverse reaction, based on the relationship with water, and that water dissociation constant. But looking at some of these questions first, the first one asks us calculate and contrast the hydroxide ion concentration in 0.200 molar and 0.200 molar. So potassium hydroxide, I should say the first time, and ammonia NH3 for the second one. So with the potassium hydroxide, since that's a strong base, it's going to be just 0.200 molar to begin with. And then with the ammonia, though, like we just saw, it's going to be a weak base. It's only going to partially dissociate. We've got to actually go through and do our equilibrium table. But with this, you may have noticed with these weak acids, weak bases that have very small dissociation constants, since they only get pushed a little bit to the right-hand side, we essentially have the same calculation every time. It's just going to be based on what that dissociation constant is. What is that initial concentration? But a lot of these look exactly the same. And we'll see that again with this one. So if we just write out the reaction even, NH4 plus, we'll have OH minus. Initial 0.200. This one we don't have to worry about because it's a liquid. 0, 0, plus X, minus X, 0.200 minus X. So when we go and actually set this one up, we're going to have 1.76 times 10 to the negative fifth. First, X squared. And then again, 0.200, just because the negative X isn't really going to affect this as that much, because it's going to be a very small change compared to the initial concentration. So when we go through and actually solve for this one, we're going to see that X is equal to, where did I put that one? 0.00188 molar. And again, if we compare that to the potassium hydroxide, that strong base, we've clearly got much, much less of this hydroxide ion. So it's going to be a much, since bases have high pHs, the pH of this ammonia is going to be lower, just because it's not going to be quite as basic. We've got less of that hydroxide ion. But it's not surprising that we get a smaller number just because it's a weaker base. It's not going to dissociate fully, so we shouldn't produce as much of that ion. Right. And then with the next one, it is essentially the exact same thing, but instead of 0.200 molar for the ammonium, it's just going to be the 0.15. So with this one, I'm not actually going to go through and work it out just for time's sake. If you want to try it on your own, pause it because I'm just going to give the answer here. So if you want to have a chance to try it by yourself, just pause it quick. Otherwise, what we're going to see, or what you should see, is that the hydroxide ion concentration for that one, and where it's at 0.15 is the initial. So we should see 0.0016 molar. And again, it's going to be the exact same setup we have here. Same Kb. The only thing that's going to change is just that initial concentration of ammonia. So on the bottom of our equation, instead of x squared over 0.2, we would just have x squared over 0.15. And then ultimately we'll solve, we'll get 0.0016 there. But like I said, we can use these acid and base dissociation constants and actually use them to relate between one another. And if we look at the reactions we have here, HA and A minus are just going to be a conjugate acid base pair. So HA is going to be the acid, A minus is going to be the base. And when we write those reactions with water, we can see the Ka expression at the top, the Kb expression at the bottom. And again, the reason HA is going to be considered an acid is because when we mix it with the water, it's donating that hydrogen. That's why we wind up with H3O plus and A minus on the right-hand side. Whereas if we take A minus and mix it with water, it's going to be a base because it's going to take that hydrogen ion from water. And that's why we wind up with hydroxide. But with each of those expressions, we don't include the water just again, because that's going to be a pure liquid. We're only interested in solutions. We're only interested in gases. So we can remove the H2O. And then we can further take this and essentially just multiply them together. And what we're going to see, if I can get the pen working, what we're going to see here is HA cancels. We have it on the top of one of them, bottom of the other. Same thing with A minus. So Ka times Kb is really just going to be the hydronium ion, which is the same as H plus, times the hydroxide ion. And that's going to be equal just to Kw, which remember at 25 degrees, at 25 degrees, that's going to be 1.0 times 10 to the negative 14th. So if we know Ka or Kb, since we also know Kw, we'll be able to solve for whatever one we're missing there. And then we'll be able to use that to help us solve different types of questions. So if we're looking at the one we have here, calculate the base dissociation constant Kb for the fluoride ion, given that the equilibrium expression for, or the equilibrium constant Ka for hydrofluoric acid is 6.8 times 10 to the negative 4th. So like we just saw, Kw is equal to Ka times Kb. And in this case, we know Ka, we know Kw, so we can solve for Kb just by doing Kw divided by Ka. And again, Kw is going to be 1.0 times 10 to the negative 14th. So if we divide that by Ka in this case, 6.8 times 10 to the negative 4th. We're dividing by a negative exponent, so we should see that the negative 14 should increase. It should become more positive. And that's why if we go through and actually solve for it, we should get 1.5 times 10 to the negative 11th. And then for the second one, it's basically the same kind of idea. It's just in this case, we're given Kb, we're trying to solve for Ka for the ammonium ion. But it's still going to be that same idea. We'll be able to, so I'll do A, B. We'll still have Kw is equal to 1.0 times 10 to the negative 14th. But now we're going to be dividing by 1.8 times 10 to the negative 5th. So what we'll see is Ka is going to be equal to, in this case, 5.6 times 10 to the negative 10. Again, this only works for the conjugate acid-base pair. So if we look at F minus and HF, the only difference between those two is that hydrogen ion. Same thing with ammonium and ammonia, NH3, NH4 plus, with just that additional hydrogen ion there. So that's why we can use this relationship. And then what we're also going to see is that certain ions are actually going to be acidic or basic. And what we'll see is anions tend to be basic because they have that negative charge. So they're going to be essentially able to kind of take one of those hydrogens from water to form HX, in this case, just that generic neutral compound, whatever it's going to be. But that's also then going to give us the hydroxide ion. And this is going to be an example of a hydrolysis reaction. So hydrolysis reaction is just something that's referring to a reaction that essentially decomposes water. So in this case, we can see it's breaking down. And then with the cations, we'll kind of see the reverse there. So since these are going to be sorry, I forgot what I was saying. But with the cations, what we're going to see is they're going to be able to react with water in a similar way, but instead of promoting OH minus, we're going to see that they can give us H plus. And the reason this is going to occur with these cations is because if we look at the picture on the left, with the picture on the left, we can kind of see with those two cations, so +1 at the top, +3 at the bottom. What that's going to do is it's going to attract the negative oxygen. And then it's got those lone pairs on oxygen, so it's going to pull the electron density towards that side. And what's going to happen is then the hydrogens are going to be more likely to dissociate. And this is going to be promoted with higher positive charges, and then also smaller size cations, because they'll be more effective at actually getting closer to that oxygen, pulling those electrons further to the right-hand side. And then when we're looking at cations and anions collectively, what we're going to see is, depending on if that ion is part of a conjugate pair with a strong base, a strong acid, weak base, whatever it's going to be, we'll be able to see how that kind of affects the pH of that solution with that ion. And then the anion, that is the conjugate base of a strong acid, will not affect the pH. So let's see. So the do HCl. So if we think about chloride ions, for instance, what we're going to see is these won't affect the pH, because when we think about something like hydrochloric acid, it's going to completely dissociate. It's going to fully give us H plus and then those chloride ions. So then if we take those chloride ions and put them with water, it's not going to then form that HCl. Because if it took that hydrogen from water, it would form HCl and then it would form OH minus. But because the chloride ion is going to stay dissociated essentially, we're not going to see it actually affecting the pH at all if we just have chloride by itself. Of course, again, hydrochloric acid is going to be the strong acid itself. But when we're looking at the conjugate base of that acid, when we're looking at just the chloride ion, it's not going to shift in the opposite direction. It's not going to reform that hydrochloric acid. So we're not going to see it affect the pH at all. And that's just going to be a similar case with the conjugate acid of a strong base. It's going to stay dissociated. It's not going to take that hydroxide from water. So we're not going to wind up with the free proton as well. So we're going to see that with the conjugate pairs of a strong acid or a strong base, they won't affect the pH at all. But when we have the conjugate base of a weak acid or the conjugate acid of a weak base, that's where we're going to see the pH change. And let's see what's a good example for that. HF would be a good. So again, with the hydrofluoric acid, we get HF. We're going to get some of that H plus, some of the F minus, but it's going to stay primarily as that molecule itself. So then if we take something like, let's say, sodium fluoride, NaF, it's going to dissociate in water. It's going to give us F minus. But what we're going to see in some cases is, I have an equilibrium there, is the fluoride ion is going to interact with that water. It's going to take off one of those protons, reform HF because it's going to have an equilibrium. And what we're going to see then is we'll now have some of that hydroxide ion produced as well. Because if we're taking that H plus from water, that hydroxide is still going to be left over. So that's why the anion of a weak acid is going to increase the pH. So remember, bases are higher pH. We're producing more of that hydroxide. We're producing more of that basic ion. So we're going to see the pH is going to rise accordingly. And then the cation, or the conjugate acid of a weak base, we're going to see is going to decrease the pH for a similar reason. So the most common weak base, ammonia, we've already seen. Its conjugate acid is just going to be the ammonium ion. So if we look at that one, NH4 plus water, what we're going to see is that ammonium is going to donate that proton. And oops, that should be equilibrium. So we're going to have NH3 now plus H3O plus. So that's why if we took something like ammonium chloride and dissolve it in water, it's actually going to become more acidic because that ammonium ion is going to interact with the water to give us those hydronium ions or the hydrogen ions, those protons, in addition to just some of that ammonia as well. And then just with some of the other ones, number 4, we already kind of looked at when we're looking at those different examples. 5, metal ions a lot of the times will be acidic, like we just saw. They're going to have that positive charge. They'll be able to pull the electron density and make the proton more acidic, more likely to dissociate. And then number 6, when a solution contains both the conjugate base of the weak acid and the conjugate acid of a weak base, in that case, we're not going to know for certain if it's going to become more acidic or more basic, because each of those substances are going to affect the pH. So it's going to be dependent on what the Ka and Kb values are to see which one's actually going to sort of take precedent, which one's going to overpower the other. in terms of directing the pH higher or lower. And then this is just a little table that kind of summarizes those things. So when we look at something like sodium chloride, if you think about it, sodium would be part of sodium hydroxide, a strong base. Chlorine, or that chloride, would be part of hydrochloric acid, also a strong acid. So the conjugate pairs of strong acids, strong bases aren't going to affect the pH. So since both of those are strong, we're going to see that's going to be a neutral solution. With the sodium fluoride, sodium is still going to be part of a strong base, so we're not going to have that affect the pH at all. But hydrogen, or not the fluoride, hydrogen, the fluoride ion, just like we saw, is going to be the conjugate base of a weak acid. So we're going to see that's going to decrease, or it's going to increase the pH rather. It's going to make it more basic. Just see the reverse with ammonium chloride. That chloride is still going to be part of a strong acid pair. So it's not going to affect the pH, but ammonium will, like we just saw. It's going to make it more acidic because that H4, or that fourth hydrogen really, is going to get donated to the water, make H3O+. So it's going to become more acidic. That pH is going to decrease. And then, like I said, with something like ammonium sulfate, where both of those ions are going to be a conjugate acid or conjugate base of a weak acid, weak base. We would have to look specifically at the Ka and Kb values for those two ions. In order to determine which one's going to be more important for that particular reaction, or particular solution, I should say. Okay, so looking at these ones, we've got a list of different salts, and we want to determine if we took these and placed them in water, would it make the solution acidic, basic, neutral, or unpredictable, meaning that we'd have to look specifically at the Ka, Kb values to determine it. And again, we just want to think about, of those different ions that would be produced, are they the conjugate base or the conjugate acid of a weak acid, weak base, strong acid, strong base, and we can use that to determine exactly what's going to occur here. So for the first one, barium acetate. Barium is going to be part of a strong acid, or a strong base rather, barium hydroxide. So the Ba won't affect it at all. But the acetate is going to be a conjugate base of a weak acid. So what we're going to see when we take this and place it with water, we're going to form acetic acid, which is going to leave the hydroxide ion free. So we're going to see that A is going to increase the pH. It's going to become more basic because of that acetate ion. That's going to be the conjugate base of a weak acid. So we're going to see the pH is going to increase. B, we've already, I think that was one of the examples on the other one, but the chloride ion won't affect it at all because it's going to be the conjugate base of a strong acid. But the ammonium ion, like we talked about, is going to be the conjugate acid of a weak base, which means this will decrease the pH. It's going to become more acidic. C, sodium cyanide. So again, sodium, just like the barium, is going to be a conjugate acid of a strong base. So that won't affect it at all. And I'll also cross out the Cl. But the cyanide, HCN, is going to be a weak acid. So this is going to be the conjugate base of a weak acid. We'll see that will become more basic then. And with these ones, I'm just crossing out the pieces that are conjugate acids or conjugate bases of a strong acid, strong base, just because those aren't going to affect the pH at all. And then for D, potassium nitrate, potassium is going to be the conjugate acid of potassium hydroxide, very strong base. Nitrate ions are going to be the conjugate base of nitric acid, a very strong acid. So we're going to see neither of those is actually going to affect the pH. And then for the final one, that'll just be unpredictable. Because the carbonate ion is going to be the conjugate base of a weak acid. We saw with the carbonic acid. And the copper is going to be the conjugate acid of a weak base. So we're going to see the copper ion would decrease the pH, the carbonate ion would increase the pH. I would guess, actually, I don't really have too much reason for that. But we would have to look to see which one of those is going to sort of take precedent based on the Ka and Kb values. So at this point, we would just say unpredictable. We'd expect it to change one way or the other. We just don't know for certain which way that's going to be without the specific Ka and Kb values for those substances. All right, and then here are just some general properties for relative strength of acids. And we can see for the most part, the strength is going to increase when we're looking at acids as we go down the table. So hydrochloric acid, for instance, is going to be stronger than hydrofluoric acid. And the reason for that is the HF bond itself is going to be stronger than the HCl bond. So it's going to be more easily dissociated, or that proton is going to be more easily dissociated in HCl. So we're going to get more of that H plus. We're going to have a stronger acid because of it. And then with the bases, would just be the opposite. So if acid is increasing down, going to be a stronger base near the top in that case. And then even with things like methane, CH4, we're going to see that those aren't considered an acid or a base, just because it's not going to produce hydrogen ions, it's not going to produce hydroxide ions, it's not going to accept or donate a proton, essentially at all. So we're going to see that those just aren't considered acids or bases. And then there's what is known as oxyacids. So it's going to be considered that because we've got the hydrogen bonded to an oxygen, and then it's going to be bonded to some other element. What we're going to see is as the electronegativity of that other element increases, the substance is going to become more acidic. And if we look at the examples we have there, we've got HOCl, HOI. So we've got very similar structures in those two. But chlorine going to be more electronegative, going to be better at pulling that electron density further to the left. And what that's essentially going to do is make the hydrogen more readily dissociated. Because if we think about the electron density shifting to the left, we're kind of taking the electrons in that oxygen-hydrogen bond and pulling them further left as well. So the hydrogen itself is going to have less of a hold on the electrons, if you want to think about it that way. So it's going to be more easy to just dissociate, more easy to get that hydrogen ion free. And that's why if we look at HClO versus HBRO versus HIO, we see the acid dissociation constant decreases as we move down that group. Just because the Y atom is going to become less electronegative, so it's pulling less of that electron density further to the left. So the hydrogen is essentially sort of more secure on that oxygen. But with chlorine, stronger than iodine, stronger than bromine, that's why we see more of that H plus being produced there. And then with these oxyacids, in some cases we'll see like with the chlorine sort of series we have, so hypochlorous, chlorous, chloric, and perchloric. Essentially very similar structures. We're just adding additional oxygens around that chlorine atom. What we're going to see is as we add those additional oxygens, now we're going to have the electron density again hold further to the left, or the right in this case rather. So what we're going to see is the oxygen and the hydrogen are going to be more readily dissociated from one another. So we're going to see more of that H plus. And that's why when we look at something like perchloric acid, HClO4, all the way on the right-hand side, that's going to be a very strong acid. Chloric acid, where we've lost one of those oxygen, is also going to be a very strong acid. But chlorus and hypochlorus, not going to have quite the electron density being pulled to the right there. So we're not going to have that hydrogen ion as readily dissociated. We're not going to have it be as strong of an acid. And that's why we see the Ka values there get smaller to the left-hand side. And then with the structures that can, with these carboxylic acids, so this is going to be a type of an organic molecule. So you can see in this case, we've got the two carbons. This is going to be ethanoic acid. And in this case, it's actually showing it dissociated. So that's why we've got the negative charge on one of those oxygens. With these substances that can undergo, or that have resonance, that resonance, remember, is going to be a stabilizing force. And what resonance is essentially just we're moving electrons, but we're not changing the way that atoms are bonded to one another. So if we look at the structures we have here on the left-hand side, what's occurring is we're essentially taking one of the sets of the lone pairs. So let me draw this so it's a little bit easier to see what's going on. But we're taking one of these lone pairs and essentially putting in that double bond. And now the carbon in that case would have 5 electron groups around it, or it would have 5 electron pairs around it. It would still only have 3 electron groups. So it would have too many electrons. It would exceed that octet, which carbon can't do. So then what we're going to do is take 2 of the electrons from that original double bond and then just move them into a lone pair on that other oxygen. So again, with resonance, we're just essentially shifting electrons without changing the arrangement of those atoms, changing anything about what's bonded to what. And with it, that's going to be a stabilizing force. So carboxylic acids that can that have resonance are going to be more acidic because they're going to be more readily able to donate that hydrogen. Whereas if it didn't have resonance, it wouldn't be as stable and would be more likely to keep that hydrogen attached to the molecule. But the resonance makes it stable, allows that hydrogen to dissociate more easily. And that's why we're going to see it's going to be a more acidic substance than if it didn't have the resonance. And then there is one additional sort of definition for acids and bases that we haven't really talked about at all. So we looked at the Arrhenius acid base, so donates or increases hydrogen ion, increases hydroxide ion for acid and base, respectively. Bronsted-Lowry is donating or accepting a proton. And then there's going to be another example, which is going to be a Lewis acid, and this is going to have to deal with electron pairs. So again, the electron or the Lewis acid is going to be what is accepting the electron pair. The Lewis base is going to be what's kind of donating them. So in this case, we can see ammonia and then boron trifluoride. So remember, boron can be electron deficient, can be okay with just 6 electrons around it. But if we look at these two substances now, ammonia has that lone pair. So it can actually donate both of those electrons, and essentially kind of take those electrons and attack the nucleus of that boron. It's going to be electron deficient. So you can kind of think about it as missing those electrons so we can form that bond there. And then based on the definitions we have, that means the ammonia, as it typically is considered a base, just now it's a Lewis base. And then the boron trifluoride is going to be the acid in this case. And then with these definitions, we'll see that the Lewis bases are going to be, or anything that's a Bronsted-Lowry base, I should say, is going to be a Lewis base as well. But with the Bronsted-Lowry bases, they're always accepting a proton. We're going to see with the Lewis bases, they can interact with other things, as we see here with the boron. And then just a couple of practice ones. So with the first one here, calculate the pH of 0.250 molar sodium acetate. And then for acetic acid, we've got Ka is equal to 1.76 times 10 to the negative fifth. So what we need to really do is think about what's occurring here. So when we take sodium acetate, we'll have the sodium ion be produced, we'll have the acetate ion be produced. And then because this is going to be a very soluble ionic compound, we're essentially just going to have it completely dissociate. So we can assume that initial concentration of sodium acetate is also going to be the concentration of the sodium ion, also going to be the concentration of that acetate ion. So what we then can do is think about which of those ions is going to affect the pH. And with the sodium, like we've seen, it's going to be the conjugate acid of a strong base, so that's not going to affect it at all. But the acetate ion is going to be the conjugate base of a weak acid. So we're going to see that that's going to increase the pH. So that's going to be the one we focus on. We'll have C2H3O2 plus water. And then it's going to form the equilibrium where it makes some of that acetic acid, which is then going to give us that hydroxide ion. And we know the initial concentration. Again, for water, we can ignore it because it's a liquid. But the other substances we'll pay attention to, plus X, minus X, 0.250, minus X. But for this one, what we've got to do is make sure that we've got the correct dissociation constant. So the value we're given, 1.76 times 10 to the negative fifth, is for acetic acid. So that's if we took HC2H3O2 and mixed it with water, we'd get some of that acetate ion. We'd get some of that hydrogen ion as well. But in this case, we're looking at, we should be looking at Kb for the acetate ion itself. So what we're going to have to do is just do 1 times 10 to the negative 14th divided by 1.76 times 10 to the negative fifth. And now we're going to see that Kb is going to be equal to 5.68 times 10 to the negative 10. So we're going to have a very small amount of this reaction get pushed to the right. But when we set this one up now, it's going to be the same as it has been in the past. We know the equilibrium constant. So I'm just going to do Kb just so I don't have to write it out again. But it's just going to be that 5.6, should be 5.68 times 10 to the negative 10th. And then that's going to be equal to x squared over 0.250. So when we go through and actually solve for this one, we're going to see x is equal to a very small number, and that's going to be 1.19 times 10 to the negative fifth molar. And that's going to be now the concentration of that hydroxide ion. So if we do negative log of that concentration, we can get the POH, which is going to be equal to 4.924. And then since we're interested in the pH, we can just subtract that from 14. And we're going to see that the pH is going to be 9.076. And with it, that makes sense because we expected the acetate ion, since it's a conjugate base of a weak acid, we expected that acetate ion to make the solution more basic, increase the pH then. So it should be a little bit above 7. And that's exactly what we see with 9.076 there. And then just for the ending, it's going to be essentially the same type of question. It's just in this case, it's actually a little bit easier because we're given the equilibrium constant we want. Because with ammonium nitrate, NH4, NO3, oops, we'll get that to completely dissociate. So we'll get ammonium ions, we'll get nitrate ions. And then with this one, it's going to be the same idea. So we'll have NH4 plus H2O. So NH3 plus H3 plus. And with this one, we look at our ice table. Again, the ammonium concentration is just going to be the initial concentration. We'll have none of that to start. We'll have plus X, so X minus X. 2. We'll take that equilibrium constant, set it equal to our equilibrium concentration, so X squared over 0.250. And what we're going to see in this case is X is equal to 1.19 times 10 to the negative fifth. So when we plug that in, negative log of that number, what we're going to see is the pH will be 4.923. And again, that makes sense because we're taking this we're taking this conjugate acid of a weak base and mixing it with water. So we should expect the solution to become more acidic. We're producing more of that hydronium ion. And that's why we see a pH of a little bit under 5, because those acidic solutions are going to have the lower pHs.